background Floer model, and he will explain us Floer theoretic mirror construction.
Okay, thanks. So it's a pleasure to participate in the conference. So the title of the talk is Floer Theoretic Mirror Constructions, and I will try to explain basically where do mirrors come from. So first, let's kind of recall. So a rough statement of what is mirror symmetry is that oftentimes you have kind of a duality where you have a symplectic manifold M, and you have and then there's a mirror dual manifold M check. And somehow the symplectic geometry of M is encoded in the complex algebraic geometry of the dual manifold M check. And the concrete example of this is you've already seen, I guess, in Mark's talk. So for example, if you take M to be the quintic threefold and you think of it as a symplectic manifold, and then there's a mirror quintic, and then you can take Gromov-Witten invariants of M. These are kind of symplectic invariants, and you can relate them to certain integrals of certain, you take the Calabi-Yau form of M check and you integrate it over various cycles, and you have a relation. So that's kind of a complex algebraic invariant. Okay, so this is a phenomenon, and then this raises a number of questions. So first, like in what way, like when we say that's a rough statement, but what is a more precise statement? In what way is symplectic geometry of M encoded in M check? But the main question for today is, given M, how do we find a mirror? And 3 is a question which we won't really talk about, but that's really the important question, is like why is it true? Okay, so in order, like I want to address mostly how we construct mirrors, but we have to have some framework for thinking about this. So we do have to start with the first question, and which is like, what is the way in which symplectic geometry is encoded in the mirror? And the answer to that is Kontsevich, the homological mirror symmetry conjecture, which I will give a statement. So suppose we are considering the case where our symplectic manifold is symplectically Calabi-Yau, which means that C1 of M is 0. Then it gives rise, this manifold gives rise to a category called the Fukaya category of M, and it's an infinity category, which is defined over a ring, so lambda R, where R is some ground ring, which we can take to be Z or Q, and what we're doing is we're looking at the Novikov ring over that ground ring, which means we're taking formal infinite sums, where we allow real powers. I guess here it shouldn't say greater than or equal to 0, just real powers. And the only requirement is that somehow that this limit, so we have it's kind of a discrete collection of real exponents where the exponent goes off to infinity. Okay, so it's a category for that. Now to describe a category, I need to say what are the objects, and then I need to say what are the morphisms. So the objects in this category are pairs, L and theta. So what L is a Maslov zero Lagrangian submanifold of M. So that's probably a concept you're familiar with. Theta is a little more difficult to describe. So theta is something which, whenever you have a Lagrangian submanifold, there's a theory which allows by FO cubed, which associates with each such Lagrangian a certain set called the Moore-Cartan moduli space of L, which I won't say anything about how it's described. But I will say that typically you can think of this space as just being, take the cohomology of L with coefficients in a certain group U lambda. And what is that group U lambda? Basically, it's a subset of the Novikov ring, where the requirement is, like we have these formal sums and require that all of these lambda i's are greater than or equal to 0. And we'll have more to say about U lambda that will feature prominently in our discussion later. So this describes the objects of the category, and then the morphisms of the category are certain Lagrangian intersection Floer homologies, Floer complexes, which I think you've seen in previous talks. The notion of the the Floer complex, except probably you haven't seen Floer complex when it depends on some this additional datum where you have these more Cartan elements, these theta 1 and theta 2. I will maybe say a word so in specific settings you can define a category which just involves data of Lagrangians, but when you define something general, you try to define this in general for arbitrary Lagrangians, you can't define these morphism spaces just for Lagrangians. You have to look at additional data. They need to be decorated by additional data of these more Cartan elements. Okay, so this is the category, and then that's on the side, the symplectic side. Then the mirror M check. We should think of it not as a complex manifold, but actually as a rigid analytic manifold, which is something which I'll try to describe later a little bit. But it's a version. You could think of it as some kind of limiting version of a complex manifold. And to such a manifold, you can associate a category of coherent sheaves. So what coherent sheaves are, suffice it to say, you should think of them as a category whose objects are roughly submanifolds and vector bundles and things created out of them. And then, so this is some category. And then the way algebraic, like the way the complex geometry of M check encodes symplectic geometry is homological mirror symmetry, which says that there's a functor mirror which maps, which is kind of an equivalence of categories between the Fukaya category of M and the category of coherent sheaves of the mirror. So basically, to each Lagrangian, you have associated a coherent sheaf on the other side, and for morphisms between Lagrangians, you have morphisms on the other side. So in essence, the real question to ask is, how do we? So I said we're going to focus mostly on the second question, which is, sorry, before I go on. So are there any questions? Please don't hesitate to interrupt me.
So the U lambda should probably have a constant term, right?
So U lambda is kind of, so U lambda is, yes. So I guess you're right. I guess it's kind of it's not what I said here. You're right. It's kind of, it's element, yeah, you're right. Such that, I guess, let me add, such that A lambda 0 equals 0, and A0 equals 1. Yeah, I think that makes it correct. Okay, thanks. Okay, now, okay, so that's the description of the category. And then, so basically the question I want to address is like, how do we come up with this mirror? So the real question is kind of, we should ask how do we construct the mirror manifold, and then how do we construct the mirror functor? And the framework for both of these is which I want to discuss, is something called family Floer theory. And I will only discuss the first question. But family Floer theory is basically a framework for addressing both these questions. Okay, and maybe let me just say a comment. Like one could ask, what counts as a good answer? Because maybe you've heard in Mark's talk there were scattering diagrams. There's like one could come up with different ways of answering this question. But from the symplectic geometer's perspective, which is not the only legitimate perspective, but it's the perspective that I'm taking, we consider kind of mirror symmetry as a tool to study symplectic topology, which means the thing we want to understand is the Fukaya category. So a good answer means an answer which helps us understand the Fukaya category or answer questions in symplectic geometry. Okay, so that's the question, and the framework I said will be family Floer theory. Okay, so how do we? So let's address this. So the general setup will be as follows. So we start out with a symplectic manifold M, whose first Chern number is 0, so it's symplectically Calabi-Yau, and the dimension is 2 times n. And then there is a smooth manifold B, which is an n-dimensional manifold. Maybe it doesn't need to be smooth. It could be more precisely called maybe a topological manifold. And then we are assuming that we have a fibration. So we have we have a map from M to B, so to half the dimension, and the fibers are required to be generically Maslov zero Lagrangians, but they're allowed to have some singular fibers over some set, which will be a thickening of a codimension 2 graph. So if you, in Mark's talk, I guess he talked about special Lagrangians. So special Lagrangians are, if you have a special Lagrangian fibration, that's a particular instance of this setup, because the special Lagrangian condition implies this Maslov zero condition. But in general, that's it's very hard to come by. And this is a more this setup is a more reasonable setup, and it's perfectly sufficient for family Floer theory. So now the answer to the question of what is the mirror provided by family Floer theory is the following. It says that the mirror should be thought of as a moduli space of objects of the Fukaya category, which are supported on the fibers of pi. Like fibers of pi, they are Lagrangians. And remember, an object of the Fukaya category is a Lagrangian, decorated by an additional datum of some point, some element of basically H1 with values in U lambda. So as a set, if we, for example, if restrict attention to the regular fibers of pi, then the part of the mirror which corresponds somehow to the regular fibers of pi is a union over all the regular fibers, and for each regular fiber we take the H1, the first homology with values in U lambda. Okay, so that describes it as a set. And the goal is, well, we want to describe it as a rigid analytic manifold. Okay. So are there any questions about what I've said?
Instead of constructing a complex structure, now we're constructing a rigid analytic. Yes.
Because indeed. So ideally, one would want to construct a complex manifold, but there are all kinds of convergence questions that we can't resolve. So we construct something which is kind of a limiting version of this. But but the next thing to explain is somehow I didn't really say what is a rigid analytic manifold. So kind of I'll try to relate the complex geometry. So we have to do a. Yes. Sorry.
Maybe you mentioned we kind of ignored the singular part, right? Or did you?
Sorry, I didn't hear the question. Can you repeat?
Sorry. So we ignore the singular fibers for now, right?
Yes, we won't discuss them. Like the single fibers, they have an effect. It's not like we ignore them because they're there. But so basically, what we're constructing is an open set inside the mirror. So if you heard Mark's talk, he said that somehow that the presence of singular fibers leads to the need to take the naive mirror and correct it. So we are incorporating, basically the idea of this talk today is to explain what are these corrections that we need to make. So the corrections are applied to. So even though we're only constructing an open set in the mirror, we already need to take into account these instant-on corrections.
Yeah, thanks.
Okay. So let's make some short digression on rigid analytic geometry. So recall we had this Novikov ring before, and then consider take the Novikov ring and remove zero from it. Or maybe I should say Novikov field. So take the Novikov field and remove zero from it, then it has a function which goes from lambda star to the ground ring. No, not to the ground ring. Sorry, it goes from lambda star to the real numbers, and what it does, it just looks at the smallest lambda I for which there is a non-zero. For which there is a non-zero coefficient. And an exercise is that if you fix some lambda in R, you ask what is the fiber of this function val, then really it's t to the lambda times the group u lambda that I wrote down, as Umut corrected me with this constant coefficient 1. So that's the fiber, and you should think of this. You should think so. You say lambda star R. You should think of it as corresponding to C star. So that's kind of a limiting version of the complex numbers minus the origin, and this function val corresponds to log of the absolute value, and u lambda is basically S1. It corresponds kind of to S1. So you could think like basically this constant. You should think of u lambda. U lambda is kind of the non-Archimedean version of the unitary group. Okay, and then when we go up a dimension, so if we can define the same thing when we have lambda star to the power of n with n components, and then we think of, and then we have a function val, which is just kind of we just apply val to each component, and this is kind of this is a formal version of what it means to be a Lagrangian torus vibration. Okay, so that's okay. So that's one thing, and then another thing. So consider if you have a rational polytope inside Rn, then to this thing one can associate a certain ring of a formal power series, and the ring is defined by taking formal sums, where AI, of course, here in this case, AI is an element of the Novikov ring. So formal sums with elements with coefficients in the Novikov ring, and of monomials where you have any kind of all monomials. So basically, this is like Laurent series with coefficients in the Novikov ring, but we have some kind of condition that if we take any point x in the polygon. Yeah, I guess, sorry, there's some, so the little I and the big I are the same index. So let me think of them as the same index. Sorry. So so you have this requirement that this sum over here goes to 0, and in order, like, what does this mean? What it means? Like, what does this condition really say? So this means that that first of all, if you put in any number, if you put in any element, like you look at the pre-image of P under this val map, and you put in any point from this pre-image, if you put it in, if you put it into into any of these monomials, then like if you put, then as you take then as as you take these indices to infinity, the valuation of the monomial goes to infinity, and valuation of going to infinity, that corresponds to being very small. So the like valuation is the inverse of the absolute value. That's how you should think of it. So valuation goes to infinity means it gets very small. Maybe here in this correspondence I should have put a minus sign. So it's minus the log of the absolute value. And there is something called the kind of the calculus student's dream, which says that in rigid analytic geometry, a series converges if and only if the general term of the series goes to 0. So this defines the set of analytic functions which converge on the set of points val to the -1 of p, and one can show that really this if we take val to the -1 of p, that's really the set of maximal ideals of this ring. So we should think of so basically we should think of val to the -1 of p as a particular local model of a rigid analytic variety, whose analytic functions are defined by this. And our goal is to construct charts on kind of the regular part of the mirror for small enough integral affine rational polygons inside the base. So I'm assuming you've seen this during the week, that if you look at the base of a Lagrangian torus fibration, it has an induced integral affine structure. So locally you can identify polygons there in kind of a canonical way up to shifts and base change of bases with polygons inside Rn. And what we want is to construct charts, local charts, which will identify the pre-image of, well, maybe I should call, it's not pi, it's pi check. So what I mean by this is we've constructed the set. So we looked we constructed the mirror as a set, and the mirror as a set comes with a function to the base because it's basically the fiber over a point is the set of objects of the chi category supported over that point. And we want to construct charts, local charts, which will take this, which a priori is only a set, and identify them with this set, which we've just described as some rigid analytic variety with some analytic functions. And we want the maps, the transition maps on overlaps, we want the induced maps to be analytic functions, that is to lie inside. So for example, if we have P, and then we have some other Q, then we want the transition function, and we want CP composed with CQ to the -1 to be in this set of analytic functions. Okay, so is it clear what I'm trying to do? Or if I went too fast, please ask me.
Well, I think it could be helpful to draw like a picture of a base with some subsets covering it, and then.
Okay. Let me do this. So, page. Yeah. So our situation. Yeah. Maybe it's too abstract. So yes. So basically, we have some manifold M, and it fibers to some base B. So this is B, and it has over except for some so you have some singular points, but then you have generic points. And over a generic point you have a Lagrangian torus. This is L, and let's say we have some point B. Now, and then we can there is an induced integral affine structure, so we can kind of so we can draw polygons. So that would be P. So P is some polygon, and then each point in P corresponds to some Lagrangian torus, and therefore you can also so we've kind of construct M check, which is we described it as a union. So we said basically we described it as a union of things like this. So let's see, LB will be the fiber. So you can think of it as also having a fibration because.
Can I just add one thing? So this H1, like it's a replacement for what people have been calling the dual Lagrangian torus.
Yes, exactly. Yes, exactly. So this H1 is going to be the dual Lagrangian torus. And this map we can refer to as pi check. And on the other hand, we have some other. So now P we can kind of identify that. Then we can go to somehow basically say R2, and we identify our P here. We identify it with with, well, let me draw the same polygon, with some corresponding polygon inside inside R2 in this case. And then there's also a fibration lambda star squared in this case, which maps to here by val. And basically we are looking, what are we looking? So first of all, we want to find some chart. So I set a chart, which is going to go, sorry, where is what I've written? So yeah, so I want to define a chart which will go. So for given p, here I have pi check of p, pi check to the -1 of p inside this space up here, and we want to define a map from this space to val to the -1 of p on this side. So we can do this in many ways, as long as we kind of preserve fibers, because we just think of this as a union of fibers. But we want to do it in such a way that if we do the same thing, if we pick another chart Q, then the induced transition function will be an analytic function. Okay.
I have also a question, which is like, can you sort of put any non-Archimedean SYZ fibration locally? Can you locally like write it always in this way, like the Darboux theorem for this other side almost?
Arnold Buell.
Yeah, but like this is like on the complex side, right?
Yeah, like a complex side version of Arnold Buell.
Yeah, I think I would say this is like, I think this is more or less the definition of what it means to be an Archimedean SYZ
Yeah,
fibration.
that's how we would say that this is the definition. Well, there are other more involved definitions.
Okay.
Like I can imagine something where somehow there's no p small enough so that you could actually get a local rigid analytic isomorphism around a point to a fibration of this form, though. But maybe that doesn't.
So, like, if you are thinking of another definition of a non-Archimedean torus fibration, then you could ask such questions. But the first, like, consider Zoidel, not the first paper who does this, they define non-Archimedean torus fibration as having such charts.
Okay.
So you need to first come up with another definition to discuss it.
You're talking about kind of the skeleton and retractions.
Yeah, I was thinking about the Berkovich space and the.
Okay, yeah.
It's not clear that you can always put it in this form locally.
Okay. Okay, so now of course there's always a naive answer. This was observed by Conservator Servan. You can always say, well, here's a naive answer. Know that so if we look like what is what is the first cohomology of an n-dimensional torus with values in u lambda? It's just u lambda to the power of n. And so there's some kind of obvious canonical identification of this union with this, because as we said before, the fiber of kind of val is canonically u lambda to the power of n. So there is some kind of naive chart which we can construct, and we will and we have to talk in terms. We have to kind of so first let's discuss a little bit this naive chart, and then we'll see the story about instanton corrections. Okay, so I just want to make an observation which will be used a lot later. So consider if you take a homology. So let's say we consider some Lagrangian fiber LB, okay, which we take B to be at the center of some polygon. Then the observation is that an integral homology, first homology class of a Lagrangian fiber. This comes out unclear. All I'm saying. Okay, an integral first homology class of a fiber gives rise to an analytic function on kind of the corresponding subset in the standard analytic torus, which in fact is a monomial function, and the function is defined as follows. So I will call it z of gamma, and I'm evaluating it at point B in the polygon, and theta in sorry, I think I meant to say something slightly different. It gives an analytic function in the chart. Like I want to basically say, if we take the naive chart, it gives an analytic function on, that's what I really meant to say. So it gives an analytic function with respect to this chart. So given a point B in the base and theta in kind of the fiber, so theta means it's a Morikawa element or this unitary one form, then we can just define a function, a number in the Novikov ring, which is which does the following things. So take t with the real exponent being given by taking well, you have gamma. Gamma is some circle which lies over B0, and then you transport it. You transport the circle over B0 to B via any chosen path that gives rise to a cylinder, and you can integrate omega over that cylinder, and that gives you a real number. And this real number is independent of the choice of this path. Different paths, if you they will give you. So that gives you a real number, which you should think of. It gives you the absolute value part of this function, and then the phase part, the S1 part, is given by, well, you have theta is by definition a one with values in u lambda. Well, you can integrate it over gamma. So this way you get a function, and and the exercise is one, that this is independent of alpha, and two is that this is really a monomial in kind of, if we take the chart that I've described before, this really gives a monomial. So this is something which we will be using later. Okay, are there any questions about this?
So B0 was an arbitrary point, right?
Yeah, so B0 is an arbitrary point, yes. So it's going to be a monomial, like changing B0 is like when I say monomial, I mean something which is, say, Z1 times Z2 times a constant. And changing this B0 will change the constant. But we should think of B0 as the point which corresponds to 0 in the chart that I'm constructing. Okay, so we've constructed a naive mirror, and we have some idea of what kind of functions are analytic, but the problem is that in general this does not satisfy mirror symmetry, except for very trivial cases such as abelian varieties. And the sophisticated answer, which is that we need to incorporate instanton corrections. So that's probably a slogan you've heard. The question is, like, how do these instanton corrections arise? And what is there, like, what does this mean beyond being a slogan? Okay, so the general point is that in general, when you have a Lagrangian fibration and you have singularities, then some of the Lagrangian fibers bound disks, and disk bubbling obstructs Floer theory. So I don't have time to kind of explain this. Like, there's a general point that you can't define the Foucault category you cannot define the Foucault category for arbitrary Lagrangians, because Floer theory is just not defined because of these bubbling. But I want to focus on dimension 4 because there's no time to do justice to this story. So in dimension 4, if you consider the case where you have the first class, the Turing class is 0, and you consider Maslov zero Lagrangians, then you pick a generic almost complex structure J, then there's no problem with defining Floer homology. That's not real. That's not the issue. However, there's a problem which I call non-invariance of Floer theoretic counts. So you can so you often have a setup. You set up some kind of Floer theoretic moduli problem, and which involves counting certain curves with boundary on your Lagrangian, and the count a priori you have to fix some almost complex structure J, and then if you vary J, then because of disk bubbling you get different numbers for different J.
Just like one picture of a Lagrangian and a disk could maybe help people.
Yes. Okay. So I wanted to describe some kind of problem, but but maybe let me. So the point is as follows. Let me really right. So let's say we have here a Lagrangian torus. And let's say this Lagrangian torus, it bounds a disk, something which kind of goes towards some singular point. So this is a disk. And on the other hand, I'm trying to define some Floer theoretic moduli problem. So which means let me maybe choose a different color. So I'm looking for something which satisfies some properties, and then it has the boundary which ends on this Lagrangian. Then let's say I started out counting it for some J for which this disk doesn't exist. Now let me not draw the Lagrangian because it makes it just confusing. So I'm just counting something like here, and then at J so I have J0, I have J1, and each of them don't bound the disk, and then for JT there is a disk. Okay, and then what happens is that so what you want to say is, Julie, if there were no disk, then what you would want to say is, well, you have some solution J0, and as you vary J, the solution persists. So typically the moduli space would look like something like so typically if you have a situation where you have, so here's J0, here's J1, and and then you have some, then your moduli problem has some solutions. Let's say you have 1, 2, 3 solutions for J0, and then J1. Then if there were no problem with disk bubbling, then the general situation would be that maybe some solution disappears, right, because it's canceling in pairs, and then another solution continues, and therefore, if you count things with signs, you will get the same number on both sides. But if at some point you hit a disk, then what happens is you could have a situation where you have a solution which goes like this, and and then it breaks. It breaks at some point into some other solution and a disk, and all of a sudden it disappears, and you can't compare the count. And the counts on both sides don't match. Okay, so that's a general problem, which kind of, if you know a little bit about Gromov-Witten invariance, that kind of, there's also a phenomenon of bubbling there, but bubbling always occurs in code dimension 2, so you can kind of avoid it, and therefore you get invariance. But when you do things in Lagrangian Floer theory, you don't get invariance. And the problem is exactly that, where it exactly occurs when you hit some disks. Okay, and I just want to describe kind of just as an example of some kind of problem, because this is the way a lot of people, at least in the beginning, people were talking about SYZ mirror symmetry. A kind of tool that they were using was the following thing. So suppose you're looking at, you have some non-compact base, and you have some partial compactification D. So it's a divisor. So you have some divisor D. And then,
full screen again, can you?
Yes. Sorry. Yes, you're right. Sorry. Also, did I not use full screen before? It was like, maybe this discussion clear? What I was? Okay, you can ask me questions.
So it's like we're counting Gromov-Witten invariance, a curve counting inside stuff, right? Inside here, the count occurs, but with boundary on the Lagrangian, let's say that's one modular problem that you could think about. And normally, symplectic things shouldn't depend on which complex structure that you choose to do this. But here, that's not true in this case. I just said more slowly what you all said.
Yes.
So,
Thanks.
So then you have to kind of account for this sum.
Yeah. And just to formulate a concrete kind of modular problem, which people use to in SYZ mirror symmetry, I think the Liaru. So you have this setup. Say you have a non-compact base, and then there's some kind of divisor, and then you want to compute the moduli space of Maslov 2 holomorphic disks. U, which intersect this divisor D, and they have a boundary on some Lagrangian L, and they represent a particular relative class beta. So that's the type of thing you want to count, and then what happens is in this base there are certain walls. So these walls, they're tori which bound Maslov 0 disks. Now these tori, you can kind of move them around. Like changing J is the set corresponds to basically can correspond to kind of moving, like taking this wall and moving it over here. And then like when you change J, since you have Maslov 0 disks here, so when you cross over here, so basically you wanted to count disks which go from here to here, and then you get additional disks, and then the number of disks changes because you also have to glue in these red disks which end on the Lagrange. Okay, so that's the type of problem which, and this is what's called wall crossing. Like wall crossing kind of changes these numbers. Okay, so this is the problem. And the solution given by FO cubed is basically that when you want to define a Floer theoretic count, you need to twist by an element by a Moore-Cartan element. Which, what does this mean? This means that instead of kind of talking about kind of a single class, like the solutions which lie in some single relative homology class, then you say you want to count disks, as I just described. So what you need to do is you need to define a function, so like so, and it needs to and what you need so for fixed J, what you would do is you sum over all solutions for that fixed J, and then you weight them by what's written here. So U gives you, so U is basically it's a disk with boundary on your Lagrangian, so you can so it has a symplectic area, and also you can it has its boundary you can use to evaluate the Moore-Cartan element, and this gives you something which lives in the Novikov ring. Now, okay. Now, what good does this do? So there's a theorem by Fukaya which says that if you have a pair J0 and J1 and they're say generic, so the count makes sense for each one separately, then if you choose a path connecting J0 and J1, then you get an induced map on the associated Moore-Cartan moduli spaces, and the thing is, like when you change, you don't just ask what is the number of solutions. You do this more sophisticated thing where you take the sum. Then this sum is really invariant if you take into account that theta for J0 corresponds not to the same theta for J1, but to a different one, gamma star. Okay, so this gamma, this is the thing which kind of brings in instanton corrections. And of course, I formulated this for this particular problem of Maslov 2 disks. It's kind of a generic statement whenever you have Floer theoretic counts, which involve boundary on a Lagrangian, then the thing you should do is you should twist by bounding cochains or twist by more Cartan elements. That is, define your count by summing over solutions with weights like this, and then changing J if you correspondingly change theta according to this map, which is called pseudo-isotopy map. You get an invariant. Okay, that's the. Okay, so does is what I said clear? Does it make sense? Okay, so now I want to just make an observation. So now let's consider a situation where so we are looking at some polygon P inside our base, and let's say we can find an almost complex structure such that with respect to this almost complex structure, the fibers over points in P bound no disks. Then if we just take the moduli space of, again, let's just focus on Maslov 2 disks representing a given class, and we consider the moduli space for one Lagrangian B, and then we consider it for another Lagrangian B prime. Then there is a one-to-one correspondence between solutions of one of them and solutions for the other. That's well, it's not okay. Maybe it's not a completely precise statement. It's not exactly a one-to-one correspondence, but the homological count is the same. But let's kind of ignore. Let's imagine that it's a one-to-one correspondence. Then, so if we take this it's not precisely true, but it's close enough to the truth for the rest of the discussion to make sense. So if we take this as a given that you have this one-to-one correspondence, then for this fixed J, the function which you can define on kind of the part of the mirror which lies over this polygon, defined by doing this thing that Fukaya says we should do, then this function in the naive coordinates that we constructed before, it's an analytic function. And the reason why it's an analytic function is, well, what do you need to say in order to say that something is an analytic function? You need to know that it's a sum of monomials, and you need to know that these monomials converge. And the fact that it's a sum of monomials is really, so maybe let me go back to the picture. So the picture is, let me even enlarge this. So let's say, let me just put points. So this is a point B, and this is a point B prime. And what we're counting are disks which start here and end on this Lagrangian. And then my claim that there's a one-to-one correspondence says that if I have a disk here, then it corresponds to another disk. Let me draw a different color, which goes from here to here. But topologically, this green disk is really obtained from this disk just by concatenating some cylinder, which I will draw, I don't know, by a different color. And the thing is, this purple cylinder, so what happens when you we consider the contribution of this particular solution? So what happens when you move around this point B? So sorry, there's B, I guess this. Let me give subscript. So this is B0 and this is B1. So when you move around B1, what happens is you take whatever you take the constant that is associated with this and you multiply it by the monomial which is associated with the cylinder, with this cylinder. So this is really a monomial. And then so this means that you have a sum of monomials, and then there are a number of ways. So one of the ways, and then kind of the convergence you can deduce from something called reverse isochromatic inequality, or you can deduce that there's some other thing which I didn't have time to discuss called the Fukaya trick. So kind of Floer theoretic counts, they give analytic functions under this assumption that I just said, that kind of locally the fibers over some points, over the points in P, don't bound any disks. And then what Fukaya says is the map that we discussed before. We said Fukaya's theorem about the existence of this map. So we said there's a map which makes this well-defined and independent of almost complex structure. Then there's an additional statement which says that this map is, so if you have kind of, if you take, what am I saying here? So if you take P, P, and you have J0 for which this property that I described before holds, and J1 for which the same property holds, namely both for J0 and J1, there are no disks in this region. Then basically for each point you have, so for each point you have a map when going from J0 to J1. And so you get some point, some map, which arbitrary is just a priori, is just a map of sets. And Fukaya says that this map is actually a map of a rigid analytic map. So, okay, does this statement, does this theorem make sense? So maybe let me draw, so imagine again, like that you have this polygon, and here you have some wall which contains disks, and then going from J0 to J1 means you're sliding this wall across this polygon, so that it ends up being the wall on the other side. So J0 corresponds to the entire polygon being on this side of the wall, and J1 corresponds to the entire polygon being on this side of the wall. So now the previous theorem that I stated by Fukaya said that if you pick any point, then this map of taking J1 to J0, it induces a map from the Moore-Cartan space associated with this point to the Moore-Cartan space associated with this point. Now basically I'm saying this thing happens for each point separately. And so there's a claim here that this map, but then basically you get a map from the union of Moore-Cartan spaces. So basically you get a map you basically get a map from pi check to the -1 of P to itself. And Fukaya is saying that this map is an analytic map. Okay, so hopefully this now makes sense. And now this gives us now the instanton, what is the instanton corrected mirror. So the idea is, well, we want to construct the mirror associated with the regular fibers. So what we do is we cover the complement of the singular values by polygons pi, and choose ji such fibers and pi bound on disks. This is kind of, I'm being a bit sloppy here. And then you can just take naive charts. The naive charts for each kind of ji, you just take naive charts for pi, and then transition maps between them use these Fukaya pseudoisotopies, and then this defines a rigid analytic structure on M check. And the important property, what makes this kind of the right answer from the point of view of Floer theory, is that Floer theoretic counts, generally speaking, give rise to analytic functions on the instanton corrected mirror. That's the okay. So now, okay, please ask questions.
Maybe you're going to the example.
Yes, I'm going to try to so I hope you'll let me go a little bit over time, or 5 minutes is kind of strict.
Yeah, just let's start and see. Yes.
Okay, let's start and see. Okay, so an example that I want to discuss is consider the focus singularity. So let's say we take so as our manifold, we take C2 and remove from it the set of points satisfying x, y equals 1. And on it, we describe a pair of functions, pi1, pi2. One function is the function x squared that's written here, and the other is the function written here. So that's a function, and this happens to be, the fact is that this is a Lagrangian torus fibration. And if you want to understand the fibers, one way to think about what are these fibers is, well, consider a function from M to like from this space to just the complex numbers, which is just take x, y to the product x, y, and then well, what do you have? Then you have somehow you remove the fiber over 1. That's what M is, and then over a general point, the fiber over a general point will be some copy of C star, which you think, and then the Lagrangian fibers that you have here, they are given by basically you take circles in here, so circles in here, and you lift them. So basically take this point over here, and then you lift it to some circle line in the fiber, and then you transport the fiber around. So that's kind of these are torus fibers. And then if you take the floor of F over 0, then instead of C star, you get a union of two lines. And then so there you get some of the fibers when you take a circle which really hits this, then if you lift this point to here, you will get a certain pinched fiber. So you'll have one particular fiber will be pinched, and the rest will also be regular fibers. So these are the tori you should be thinking of now. But now, if we want to think of it, the base as a torus fibration, so now we're changing the picture, and as a torus fibration, this fiber projects to R2, where we have the functions mu, which was what I called before pi 1, and lambda, which is what I called before pi 2. And what happens is that the singular fibers, so we said that F has some singular fiber, and that singular fiber projects to a line. And this is basically so for the standard almost complex structure, this is the only line for which the tori bound holomorphic disks. Of course, we can kind of by changing J, we can kind of make this line move around. So in general, every fiber that's in any point which is not on the line does not bound holomorphic disks, and these ones they bound holomorphic disks. So now, so this is a situation which is sufficiently easy to kind of compute everything, for which one can actually work out what is the mirror. And the way we work out the mirror is by taking this principle that we said before, that Floer theoretic counts are supposed to be analytic. So if you want to go, you can go read a paper by Denis Roux, where what he does, he analyzes the problem the Floer theoretic problem that I described before. You take Maslov 2 disks and you compare kind of Maslov 2 disks on one side of the wall to Maslov 2 disks on the other side of the wall, and just by the ansatz that those things are analytic, he deduces that he works out what is the transition function associated with wall crossing. I will say something slightly different. I hope it will not take more than 2 minutes. So we want to figure out the transition maps, and so the kind of moduli problem for doing this that I will use is Hamiltonian Floer theory. So basically, if we take a Hamiltonian H from our symplectic manifold, then it gives rise to a certain complex, and that complex gives rise to a Floer homology, which is the Floer homology of this Hamiltonian H. And then we can pick a class in H, and we can use it to define moduli problems, which are called closed open moduli problems. So basically, if you give me a fiber B and you give me a Mercaton element, what I'm going to do is I'm going to count closed open trajectories. So what this means is that I'm counting disks which have an interior puncture, and you have gamma. The interior puncture maps to my class gamma, and the boundary maps to my Lagrangian fiber B. And I'm just using the ansatz that this defines an analytic function of the mirror. Okay, now as we spoke before, there is kind of a naive mirror. So if we pick a basis, so again, let's go back to this picture. So we have this base, and then so we can talk about a chart which lies on the right and a chart which lies on the left. And we can pick. So if we pick a basis, say for the chart on the right, what does it mean to pick a base for the chart on the right? It means to pick generators for the homology class of a Lagrangian fiber. Then this gives rise to a pair of coordinates on the naive mirror, on the naive chart on the right. And then if we kind of take, so now if we take these two generators, we can transport them to this side, we get an additional chart on the left. And we'll call this chart W1 and W2. So coordinates here are Z1, Z2, and coordinates here are W1, W2. Now, if we, okay, so these are charts, and we want to understand, so basically, as I said before, this wall is something you can move around. So basically, we're asking, so we can think of them as having some kind of overlap. And then we're asking, how do we express Z1, Z2 in terms of the coordinates W1, W2? That's basically the question we're asking. So, so if we carefully choose our Hamiltonian H, and we choose our classes, the homology classes, right, then we can set things up so that the function corresponding, this open-closed function that I wrote before, corresponding to the moduli, the open-closed moduli problem. So in the right chart, the analytic expression for it is just that it gives so gamma I gives me the coordinate zi, and we want to understand what this same function is when I express it in the chart on the left. So let's consider f gamma 1. Yes.
Well, I think maybe we should wrap up. I don't think. Yes.
You think nobody's understanding? Okay.
It's already two minutes past. I think we'll probably need 5 more minutes at least to discuss that. Right? I think it might be good to just tell people the result of the computation, and then they can look at your notes.
Okay. So the result of the computation is that that when you compare, so you have these two, you have these two functions, f gamma 1 and f gamma 2, and when you evaluate, so f gamma 1 is the one which corresponds to kind of the function which kind of measures flux in kind of, there's the monodrome invariant direction. So it's the one which, so f gamma 2 corresponds to measuring flux in the of the monodrome invariant lines. So f gamma 1 is kind of the one which goes in this direction, kind of transverse to the wall. And so the bottom line answer is that when you express this function, you get an answer which says that the expression of Z2 in terms of W1, W2 is given by let me make this large. The answer is Z2 equals, sorry, it's W2 plus W1 times W2, and Z1 equals W1. And which, if you think about it, what this transition map means, it means that you recover, you get the mirror. The mirror is the same manifold as the one you started with in this case. Okay, so that's the answer, and hopefully my notes.
And the wall cross, like maybe can you also factor out the 1 plus W1, because people have seen it in that form, W2 times 1 plus W1. We've seen this wall crossing transformation in like many different walls. It's the same.
Okay. So yeah, I guess I'll stop here.
Okay, let's thank you, Al.
and we're gonna close the node. So, I mean, there's some non-trivial stuff happening that leads to this result.
Mhm.
So you should get.
Okay, question, problem?
So I didn't quite understand like the resolution of how like you had this problem when you varied J that the modulus plus counts were different. Can you just go back and like explain how we resolve that problem?
Sorry, I hear like I'm having great difficulty hearing.
No, could you explain how did you resolve the issue of like the moduli space counts being different when you like varied J in a one parameter family? The resolution.
So the way it's, I mean, there's a so the resolution is that you kind of, what happens is that when you bubble, like when a disk bubbles off, there's the number of solutions changes, but at the same time there is some compensating change, like this map, this pseudo-isotopy that Fukaya defined. It gives a change kind of, because you weighted it by this one form, then there is a change, like the one form changes in a way that compensates for this disk bubble. That's.
Can I try another maybe simple answer? Like I think this is just essentially computing how the counts change. You know that the counts change, and you now say that, okay, I know that the counts essentially change by this formula.
Well, what can I say?
I mean, is this somehow similar to this Wendell bifurcation thing, stuff like that? Like, is that something similar to this? Like the bifurcation and Wendell's.
No, give me a second. Just give me a second.
I just don't know Wendell's bifurcation.
So, like, what you should think of the maybe something. I don't know if it gives a good enough explanation, but what you should think of is as follows. So you have a Lagrangian. I mean, in 3 dimensions, I don't know if in 2 dimensions this is a good way of thinking about it, but you should maybe you should think of this time parameter as some, like it's living in some one dimensional higher. So at least in 3 dimensions is a good way of thinking about it. So you should think of like, say you have you're trying to count you have some moduli problem, and then you have a disk, and the Lagrangian bounds a disk. And then what happens is when this solution hits the disk, what happens is you get a change in the linking number between the boundary of the disk and the boundary of this moduli space thing that you're counting. So a change in the number of disks on the one hand corresponds also to a change in some linking number. So if the thing you were counting were say solutions, number of solutions plus linking number, then when the number of solutions change, the linking number also changes in a way that cancels the discrepancy. I don't have a better answer than that. Maybe Umut?
Well, I can try explaining more after the talk.
Maybe. Okay.
Okay, another question?
Yes.
Maybe one, like, so you start from A side and you construct this rigid analytic space, right? That's the. So what's the statement here about? Is it B side now, or this new construct?
So, for example, in this example, I made a statement which says the B side, say if this manifold that I said in the example, then the B side is actually the same as the A side. So in this particular case, the rigid, in this particular case, the focus singularity is self-mirror. That's it will not definitely not always be the answer.
This is not complex structure.
Yeah, but there is still a category of coherent sheaves.
Okay, so
Which is on a
same statement holds for.
Yes, but you have to make definition correctly.
Okay.
But there is a definition of coherent sheaf on a digital space. And they form a category. There is a theory of this.
And then this construction, does it prove this homological mirror in this case, or it's just?
I mean, then you have to.
Oh, this is just the first step. I mean, then you have to like this is just what is the space, and then you have to construct the mirror functor. So.
Okay. Thanks. Any question from online participants? Okay, let's thank you all again.